Hello everyone. Today's lesson is on 8.5, solving exponential equations. Just make sure that you always keep in mind one very important concept when it comes to solving the exponents. You should try your best to look into both sides of the equation, and if you can make both sides with the same base, then you can solve the exponents. So for example, if you have your worksheets that you can follow me along, when you get a question like 3 to the power of 5x equal to 9 to the power of x minus 1. So think about how the base of 3 and the base of 9, what they have in common. Okay, so so between 3 and a 9, if I can use that as a 3, but the 9 will be a 3 to the power of 2. So what they have outside or originally still be the same. Okay, so now once they have the same base, then I can say their exponents must be the same. So their exponents will be when you distribute this 2 into the x minus 1. So what I have here is the left side, I have the exponents of 5x, but on the other side, when you distribute this 2, you get a 2x minus 2. So rearrange everything, you get a 3x equal to minus 2. So x has to be equal to minus 2 over 3. Okay, so this example is very straightforward. The only thing you have to pay attention to is that when part of the exponents is a binomial, then make sure that you need to distribute this. You need to distribute this into each of them. Okay, so example B, when you have the base of a half to the exponents of x plus 4, and the other side is 1 over 16 to the exponents of 3x. Okay, now I just want people to pay attention to whenever you see a 1 over something with the exponents, that in fact is the same as a 1 over 16 with the same exponents 3x, because 1 to any exponents will still give you the 1. So that's why you can either write it like this or you can write it like this. Okay, so between the two, and because 1 is 2, 1 is a 16, well, this one is a 1 over 2. So this can have a base of 2, but with the negative 1. Okay, 2 to the negative 1 will give you the 1 over 2. And over here, for the 16, if I have a 2 to the negative 4, then I know that 2 to the negative 4 will also give me the 1 over 16. But I still have my exponents outside, of course. So this will be a 3x. Over here will be x plus the 4. Okay? So now with the same base, I can say that their exponents must be the same. So again, this exponents need to be distributed, okay, and same as this one. So now I can say a negative x minus 4. When you distribute a negative 4 into x plus 4, you get a negative 4 minus 4 equal to a negative 4 times the 3x, give you a negative 12x. Okay, so this one here, you will end it up with the 11x, that is equal to 4 after you rearrange everything. So x must be equal to 4 over 11. So this is the answer for the B. And for C, simple, between the base of 9 and the 27. So I can change both base in terms of base of 3. So 3 to the 2 will give you the 9. And the 1 minus 2x remain the outside. And 27 will be a 3 to the 3. And the minus 2x still goes outside. Now once we have the same base, then now I can distribute this exponents into a 1 minus 2x. So that will give me a 2 minus a 4x must be equal to a negative 6x. Okay, and when you rearrange everything, that will be a 2x equal to minus 2, and so x must be equal to minus 1 for the part C. Okay, Done. And the next one, D. When you have a fractions, okay, equal to some number on the other side, but if you look at all the base, okay, between 8, 4, and 32, I can certainly turn everything in terms of base of 2. So 8 will be a 2 to the 3, and you still have the exponents of x minus 1 divided by 4. I can turn this into the base of 2 to the power of 2, and I still have a 2x outside, and equal to, and 32, I can turn this into the base of 2 to the power of 5, and I still have my 4x out there. Okay, so now so on the left side you should end it up with a 2 with the 3x minus 3. Okay, but because they have the same base, so that means this exponents of the numerator should be subtracting the exponents of the denominator, which is a 4x. Okay, so I don't have to write this into a fractions anymore. Equal to, this is going to be 2 to the exponents of 20x. Okay, so this will be the part D, and now I can solve for the exponents. And the exponents, when you collect all the exponents, you should have a 3x minus 3 minus 4x, that's equal to 20x. Okay, and when you look at all of this, and at the end you should end it up with the 21x, that is equal to negative 3. So x must be equal to negative 3 over 21, and then you reduce it to a negative 1 over 7. Okay, so this will be your final answer for D. And moving on to example 1E. Now, example 1E, when you have a root 27 here on the left side and then a 3 root 3 on the other side, but as a denominator. But usually we would like to change the radical sign into the exponential form. But because I know that the root 27 in fact can change into the same base at the other side as a 3 root 3, because then the 9 times the 3 will give you 27. So when you fully simplify this radical, you get a 3 root 3 and to the exponents of x plus the 5. Okay, and over here, even though this is a fraction, but a 1 over 3 root 3, you can say that this is a 3 root 3 to the negative 4x. With the extra negative, that makes it a 1 over. Okay, so that is how quickly I can turn both sides into the same base. So now I can say the exponents x plus 5 is equal to minus 4x. Okay, and so when you solve, when you rearrange everything, you will have 5x equal to negative 5. So x must be equal to negative 1. Okay, but if this is not going to be the same as the 3 root 3 over here, then usually I would turn this into an exponential form, and then I will evaluate from there. Okay, so you always pick the method that will quickly do the job. Okay, now for the F, it's a slightly different because you have the variable terms for more than one terms there, like on one side. So this is not like one terms equal to one terms on the other side. For this one here, we need to break down the x plus the 1 into a 5 to the x times another 5. Okay, because according to the exponential law, when you multiply two terms with the same base, you add the exponents. And this 5 here with the exponents of 1, so that is the reason why you have a 5 to the exponents of x plus the 1. Okay, And so I'm adding a 5 to the x equal to 150. So now on the left hand side here, you get to see there is a common factors 5 to the x. So think about this 5 to the x as an a. So you have a 5a plus another a. So you ended up with the 6a, right? So it's either way. If you can see that there is a common factors of a 5 to the x, then you can take out the common factors over here, and then you will have a 5 and plus the 1. Okay, because when you distribute this, you get the 5 times the 5 to the x plus the 5 to the x. Okay, that's equal to 150. And knowing that this will give you 6, but when you divide both sides by 6, so you ended up with 5 to the x equal to 150 divided by 6. Okay, and this you will get into 150 divided by 6 is going to give you 25. So now that will be easy now, because 25 can go into a 5 to the power of 2, so therefore x must be equal to 2. Okay, so this F is a different kind of question that that we have to use a different technique to break down the exponents when it comes to a binomial. Okay, and so because you have more than one terms on the left side, so it's not like the previous example where you can turn both sides into the same base. Okay, so for G is kind of a similar with F. Okay, if we look at the 3 to the power of x plus 3, we can break this into a 3 to the x times a 3 to the 3. Because when you multiply two terms with the same base, you add the exponent. So that is how you get x plus the 3. Okay, and minus another 3x, 2 to the x here, and equal to 26. And again, I do see the common factors here, so I will take out the 3 to the x. Okay, and 3 to the 3 will give you 27, and minus the 1. Okay, so when you distribute this, you're going to get back the same, equal to 26. And you know that 27 minus 1 will give you 26, and we need to get rid of that by dividing both sides by 26. So you ended up with a 3x is equal to 26 divided by 26, which is a 3 to the x, give you a 1. And the only things that you can get 1 here is when you have a 3 to the 0. 3 to the exponent of 0. So therefore, the x must be equal to 0 here. Okay, the exponents over here. So that will be example 1G. Now, moving quickly, let me see if we can quickly finish the example 2A. So example 2A is when you have an equation, okay, that you have a 13 equal to 15 times a 1 over 3 to the power of 1 over x, okay? Now, this is the kind of example that when the same base is not possible, okay? So when the same base is not possible, so first of all, we need to isolate the variable terms first. So the variable term, the x, is attached with this. So that means let's get rid of the 15 by dividing both sides by 15. So you ended up with a 13 over 15 equal to 1/3 to the power of 1 over x. Okay, so part of your exponents could be fraction. Okay, so in this case, because I cannot turn 1 over 3 and a 13 over 15 into the same base, is too complicated. They don't even have anything in common, like the 3, the 9, the 27, or the 8, the 16, or the 32. So in that case, this is when you have to take the log for both sides. So when you take the log, that means you multiply the log on both sides, okay? And remember the power law, okay? So this one is fine. So log of a 13 over 15 with the base of 10. Okay, whenever you're taking the log, then assuming that both sides must have the base of 10. And this one here, I will bring the, because of the power law, I can bring down the exponent, so 1 over x times the log of 1/3. Okay, now I can solve. Now I can solve for the x by, first I have to divide both sides by the log of 1/3. So when I bring this over, I have a log of a 13 over 15 divided by log of a 1/3. Okay, so that I will have that. But because solving for x, so I need to kind of reverse everything. Okay, so when you reverse everything, so x must be equal to log of a 1/3 divided by the log of a 13 over 15 in exact form. So this is the exact form, but if you need to turn this into approximate form, so you can use your calculator, taking the log of 1/3 divided by the log of bracket 13 divided by 15, you will get approximately 7.68. Okay, so this is going to be the final answer, one in exact form and one in approximate form. So depends on the questions. If it doesn't ask for specifically form, then I would just leave it in exact form. Okay, usually. Part B, 2B is when you, again, you have an exponents, the x here on, and the other side is there, but as you can see, between the 4 and the 7, there's no way that you can make both base the same. So when you have to take the log for both sides, like what we did above, so you're taking the log, and once you take the log from both sides, then the base is going to be the 10. Okay, so you're taking the log of 1 over 7x minus 4. Okay, and what you do over here is that you can bring the you can bring the exponents outside. So you have a 5x plus the 3. Okay, I will put in the bracket times the log 4. Okay, and for this one here, oh, you know what? Maybe I should, let me just quickly redo these questions so that I don't have a fractions. I don't have a fraction. So if I will I will look at this one here. The 1 over 7 to the exponents of it will be like 7 to the negative of x minus the 4. Okay, yeah, I think this is the better way to deal with it. Okay, if so that I don't have to, so when I doing the taking the log for this end, okay, I can show you. So if I'm making this into that form, so now I can have a minus, well, I'm taking the log of a 7 of a minus x minus 4. Yeah, that is what I'm supposed to do in the beginning. Okay, and well, I can continue from here. Then I'm going to take the negative brackets x minus 4, okay, as a log 7. Okay, like this. So I don't have to deal with the fraction. That's the whole idea. So from a 1 over 7 to the power of x minus 4, I turn this into a 7 to a minus. because this is minus will give me the 1 over, okay, with the same exponents x minus 4. So this exponents here will becomes, according to the power law, I will bring it all the way in front of the log 7, okay? And then, because this is a binomial times the log 4, so this, I need to distribute it, okay? I need to distribute this, and I need to distribute this. So this one, I will be getting, what I will be getting is the following. I will get a 5x times a log 4, and then plus a 3 times a log 4. Okay? And on the other side, so when you distribute the negative x with the log 7, so you get a negative x log 7, and a negative 4 becomes a positive 4, so adding a 4 log 7. Okay? So now, what we have, I want to show you that where the x is. Well, the x terms is this one and this one. The other terms that has no x, they are just like a constant. So I will need to gather all like terms together. So I'm going to put all the x terms on one side. So I have a 5x times the log 4, and then plus, so I have 5x times a log 4, and then plus x times the log 7. So I'm bringing this over, but at the same time equal, I'm going to bring this over to the other side. So a 4 log 7 minus a 3 log 4. Okay, so those are the two terms that without the x, so they are the constant. Okay, and we're not going to evaluate anything yet, but from here, I need to take out the x as a common factors. So I'm going to have a x, okay, and I'm going to multiply by a 5 log 4 and plus a log 7. That's equal to all of this. Nothing changed on the right hand side, but now once I factor the x out, then in order to isolate the x, so the x is going to be equal to, okay, I need to divide both sides by the 5 log 4 plus a log 7. So everything over on the right hand side, 4 log 7 minus a 3 log 4 divided by 5 log 4 plus a log 7. Okay, so I hope you can see that clearly. And now in the final step, you can do it on your calculator. Okay, you can do it on your calculator, and the answer in approximate form is going to be equal to 0.41. Okay, so this is going to be your final answer for this part. It seems to be long, but and be extra careful when you carry some of this term down. Okay. And finally, for the last questions, the last example, when you have 3 to the 2x plus 4 equal to 5 times the 3 to the x, okay? So this one, unlike the one with the adding for the exponents, so this is not, you cannot break this into a 3 to the, well, you still have to break this into a 3 to the x. But the thing is, in order to have 2x, then you must have a power of a 2 outside. So it's not another 3, okay? So I want you to see, okay, when I bring the other terms minus a 5 over 3 to the x from the other side plus the 4, then what is left on the right hand side is 0. I'm bringing everything over on the left side. But I want you to see when I break down this, and as you can see, if I have a 3x to the power of 2 minus 5 of the another 3x and plus 4. So if you let, this is the kind of question that I will let a be equal to 3 to the x. Why? Well, then I can rewrite this question as a to the power of 2 minus the 5 times the a plus the 4 equal to 0. So now it looks like that I'm going to get a simple trinomial, okay? A simple trinomial, when you factor this, you can solve for the variable. So this one is a minus the 4 and is a minus the 1, okay? Negative give you a positive 4, negative a and a negative 4a give you a minus 5a, okay? So in fact, a should equal to 4 or a is equal to 1. So that makes the questions a lot simpler. But in fact, we're not solving for a, we're solving for x, right? So now, once I know what the a is, I can replace the a with the 3 to the x, because a, in fact, is equal to 3 to the power of x. So when 3 to the x is equal to 4, or 3 to the x is equal to 1, now I can solve for the x by using the log methods. So x is equal to, if I taking the log for both sides, then I should have a log 4 divided by a log 3 for this part of the x. Okay? And for here, in order for 3 to the x is equal to 1, then x, 3 to the x must be equal to 3 to the 0. So x must be equal to 0. Okay? So you will have a two different answer here. You can turn this into approximate form, but usually we want you to leave it as an exact form. Okay? So this will be the last example.